copy of the note catcher from yesterday? Anyone who doesn't have it, was absent, misplaced it, anything like that? I have a bunch of them. You're going to want to get the notes from a friend if you missed the first part. Anyone else need a copy? So the quiz from yesterday, I've decided that I'm unable to count that as a grade because the answers were compromised. So in future quizzes or test situations, I'm requiring everyone to put their phone into the door pocket. You need to check it in at the beginning of the test, and then you can get it after you're done. But I had students who took pictures of the test and then distributed it to people in different periods, which makes it an inauthentic assessment. So instead of having that be a grade, I'm going to have a more cumulative exam later on in the unit, and I think that that'll be a little bit more accurate. So 3 forms of energy transfer. Conduction, convection, radiation. We went over these a little bit earlier, but we're going to go a little bit more in depth and then look at the definitions and gain maybe a deeper understanding of those. So conduction is the transfer of heat through matter by molecular activity. Heat always flows from areas of high energy to areas of low energy. You'll never ever see an example of heat flowing from an area of low energy to high energy. So the reason why conduction is different from radiation, we're going to kind of look at the distinction between these two things in more detail today. But it has to do with the kind of energy that's being transferred. So if you recall from yesterday, the first law of thermodynamics, that energy it's not created or destroyed, it only changes forms. Different forms of energy move by conduction, and then other forms move through radiation. It depends on whether it's heat or light and how that gets transferred. Certain substances are better conductors than others, and so you'll see heat moving more quickly through certain substances and less quickly through others. That's why we have materials that insulate and materials that conduct. Metals are much better conductors and they feel a lot hotter than insulators, like a ceramic coffee mug. We use ceramic for a reason, because it keeps the heat in, right? It doesn't conduct heat very well. Once we move through this section of types of heat transfer, we're going to be talking about the electromagnetic spectrum, which I think is a lot more interesting than this section. Then convection. The definition of convection is the transfer of heat by mass movement or circulation within a substance. So we talked about conduction within the context last semester of the molten rock that exists in the mantle. You have the hottest magma rising to the top of the mantle, cooling off a little bit, and then sinking back down. So that circulation causes the movement of the tectonic plates. They're basically sitting on top of boiling magma that's circulating and causing those plates to move. We also have convection currents in the atmosphere, and we have have convection currents in the ocean. So just like I was saying earlier, we have it in the air, which is in the atmosphere. We have convection currents in the ocean and in the mantle. It takes place where molecules are free to move. So you don't see convection currents happening in solids. You see it happening in fluids. And if I use the word fluid, that means I'm talking about a liquid or a gas, because those molecules move around more freely. But solids, the molecules are structured and they don't move around at all. Okay, so this is where we're kind of hitting the meat of the material for today. Who here has heard of the electromagnetic spectrum before? I think I've talked to a few of you about this, but if you haven't heard about it, that's totally okay. When we talk about electromagnetic waves differ in their frequency and their wavelength. I think that's a blank on your note catcher that I didn't include on the board, but they differ in their frequency and their wavelength. And what I mean by that is we have several different types of electromagnetic waves, going from radio wave, like with the least amount of energy here on the left and the most amount of energy here on the right. You have radio waves, microwaves, and infrared waves. In the middle is the visible spectrum, so this is what we see. These are all the colors that we see, and the colors vary based on their frequency and wavelength. And then the higher energy here on the right, which is ultraviolet, X-ray, and gamma rays. So if I were to draw a few different types of electromagnetic waves, it would look like this. Let's find a good marker. So we refer to the shape of waves by looking at this baseline. And if you have a wave that's shaped like this, then the wavelength is how long for it to do, to go up and then back down and then back up one more time. So the wavelength would be this distance. Now if I have a different wave that has a shorter wavelength, the wavelength would be that distance, but the frequency refers to how many times it crosses over the baseline. So this one crosses over less frequently, which means that its frequency is lower. This one crosses over 4 times within the same time span, which means that its frequency is higher. So the higher the frequency, the higher the energy. Over here on the right, these are gamma rays, and their frequency is a lot higher than these low energy waves here on the left side. Within the visible spectrum, red has the lowest frequency and purple has the highest frequency. So that means that red is the lowest energy light and purple is the highest energy light. And the whole spectrum has everything in between. Are there any questions about that? No? This is just another depiction of how these frequencies and wavelengths differ between different waves in the spectrum. So like here, gamma waves, you can see they have a really high frequency. They're really close together. The wavelength is really short and they're crossing over a lot of times. And then visible light is kind of like in the medium energy area where their frequency is less than the gamma and the X-rays. And then radio waves have a really small frequency. So you have all the way from like 10 to the minus 9th micrometers, which is where they're crossing over a lot of times in a very short amount a very short time span, all the way to like radio waves have a wavelength of up to 1 kilometer. So they're really not vibrating that much. So then how does this apply to the atmosphere? So the sun gives off radiation all the time. And I think we talked yesterday about how the heat from the sun isn't actually what heats the earth. It's the light energy that's given off, because that light energy hits the atmosphere and turns into kinetic energy, or the motion between the molecules that are in the atmosphere. So radiation is the energy that comes from the sun, and when it is released from the sun, it branches out in 360 degrees, and it reaches the earth in the form of light, which is then transferred into kinetic energy or heat. Seems like a small distinction, but it's important. Does anyone need more time on this slide? A couple people? Okay. If I stand here, is that blocking the screen at all? No?
Thank you for asking.
Okay, so there's 4 laws that govern radiation, and the reason why these are important is because it dictates how the energy from the sun interacts with our atmosphere and how that affects climate and weather. So the first law is that all objects at any temperature emit radiant energy. The hotter the objects radiate, the more total energy per unit area than colder objects. So if you have an object that's a very good conductor and it is able to conduct a lot of heat throughout its mass, that means that it's also going to be emitting a lot of radiant energy. The third rule is that the hottest radiating bodies produce the shortest wavelengths of maximum radiation. So since the wavelengths are shorter, that means that the frequency is going to be a lot higher, and therefore the energy of the radiation is going to be higher. So the hottest radiating bodies produce the most energetic radiation. And then the fourth law is that objects that are good absorbers of radiation are good emitters as well. So if they can absorb a lot of radiation, that means they can emit it as well. So in relation to our atmosphere, the oxygen and nitrogen are really good at absorbing radiation. That means that they're also really good at emitting it. But if we continue to add greenhouse gases like carbon dioxide and water vapor and methane to the atmosphere, then that means that that heat that gets absorbed isn't going to be able to be emitted as well. So there's kind of a give and take here. you need a little bit more time on this slide? Cool. Okay, so in relationship to the atmosphere, there's a few things that happen to solar radiation when it hits. So some of the energy is going to be absorbed by the atmosphere. So like if this is the atmosphere and this is the Earth, and you have a bunch of little molecular particles in here that make up the atmosphere. So some of it is going to hit and it's going to be absorbed by the atmosphere. Some of it is going to pass through and hit the Earth and be absorbed by the Earth. And then some of it's going to hit and it's going to bounce off and be reflected. Now the contents of the atmosphere would determine how much of that gets reflected, how much of it gets absorbed. So as far as the numbers go, 30% of the solar energy that reaches the atmosphere is going to be reflected back into space, and it's not going to be absorbed by any of the molecules in the atmosphere or be absorbed by the Earth. 50% of the solar radiation is going to be absorbed at the Earth's surface, and it's going to arrive as scattered light. So what I mean by scattered light is that I'm going to redraw this diagram of the Earth one more time. So you have molecules that make up the atmosphere, and some of the light is going to hit and it's going to bounce off. Some of it is going to hit molecules of atmosphere and it's going to be absorbed by those molecules. About 20% will be absorbed by the atmosphere. The other 50% is going to hit and be absorbed by the Earth's surface. And it's scattered light because not all of the light that hits the Earth is going to make it to the surface of the Earth. It's going to be either absorbed by the atmosphere or reflected back into space. So I just covered that part of the words there. How much of this is on? Okay. So I'm going to talk a little bit about the greenhouse effect, and I'd like you all to just write down quickly this definition of the greenhouse effect. So it's the heating of the Earth's surface and the atmosphere from solar radiation being absorbed and emitted by the atmosphere, mainly by water vapor and carbon dioxide. So the more carbon dioxide and water vapor, I'm actually going to add another molecule to this definition, because methane is a really potent greenhouse gas, about 4 times more potent than carbon dioxide. And when you have radiation that's hitting the atmosphere and bouncing off, it's likely that on the upward trajectory, it's going to hit another molecule like carbon dioxide and bounce back towards the earth and then be absorbed. So these gases shift the amount of heat and the amount of radiation that can actually escape from the atmosphere. And there's a pretty good diagram that shows this on the next slide. But basically, the atmosphere exists in this very delicate balance. And the more you change the contents of the atmosphere, that changes the insulation. So if you have heat that's supposed to be reflected out into space, and then as it's being reflected out, it hits a molecule of some sort of greenhouse gas and then gets reflected back to the earth, that energy is going to be absorbed by the earth, and it's not going to have a strong chance to escape.
Is that how global warming is called?
Yeah. So the greenhouse effect is what causes climate change. I think global warming is kind of an outdated term at this point because it doesn't necessarily mean that the whole earth is going to get warmer. But what it does mean is that the kinetic energy of the atmosphere is going to increase. And so when the kinetic energy contained within the atmosphere increases, that's going to increase, it's going to increase extreme weather events, it's going to make them more extreme, and it's going to make them more frequent, and it's going to make weather less predictable. So that all is really bad because it has a whole cascade of other events that are occurring. Do we need a little bit more time with this definition? Okay. So this is the last thing I'm going to show you guys. This is kind of what I was talking about, like radiation that's coming off of the earth. Because remember, one of the laws about radiation is that objects that absorb a lot of radiation also emit a lot of radiation. But that emission won't occur unless it can escape from the atmosphere. So the more greenhouse gases absorbed, the radiation will continue to bounce off and be trapped before it can escape. It'll just take a lot longer for that radiation to escape. So, in conclusion, greenhouse gases will warm the planet. Decreases in greenhouse gases will cool the planet. And this is a list of greenhouse gases. That's all I have for you guys today. I think we finished like 5 minutes early. So, thank you guys for being patient. Tomorrow we have an energy lab. And I know we've had 2 days of notes in a row, which is not fun. But tomorrow you'll be moving around. You'll be moving from table to table, going between stations, and we're going to be playing with all the batteries and circuits and solar panels and all those things that I've been trying to figure out for the last couple weeks. So I think that you guys will hopefully have a little bit more fun in class tomorrow than we had today.
You need the front, right? Or do you need the back? Can you, well, we're going back here.